It's happening again. Satellites are detecting measurable strain building along a 4,000-kilometer fault off South America's coast, the same boundary that unleashed a magnitude 9.5, the largest earthquake ever recorded. GPS stations show the coast bending. A century-old seismic gap is locked and loading fast. Scientists warn the strain now mirrors past megathrust buildup, and it may not hold much longer. And here's the twist. 40 million people are living directly above it. This danger has a name. It's called the Nazca Plate, the world's most violent plate boundary. Far below the Pacific Ocean, a massive slab of dense oceanic crust is advancing towards South America at nearly 9 centimeters every year. This slab, known as the Nazca Plate, is not drifting calmly across the seafloor. It is colliding head-on with the South American plate, forcing its way beneath the continent in a violent process called subduction. This grinding boundary stretches roughly 4,000 kilometers from Ecuador through Peru and into Chile. It has carved the Peru-Chile Trench into the ocean floor and pushed the Andes Mountains high into the sky. This collision is anything but gentle. The plates are jagged and fractured, and when they meet, they frequently lock. Motion does not stop. Instead, it is stored. The energy builds quietly beneath cities and coastal communities. GPS stations anchored along the margin show the continent warping millimeter by millimeter as the Nazca Plate keeps advancing and South America continues to resist. It is one of the fastest subduction zones on the planet. That speed is critical. Rapid convergence allows immense strain to accumulate when the boundary is locked. Over decades, the stored energy can grow into something capable of rupturing hundreds of kilometers of fault in a single, devastating release. The Andes are living proof of this relentless force. They are rising because the continent is being compressed and thickened as the Nazca Plate dives below it. Volcanoes such as Cotopaxi in Ecuador, Sabancaya in Peru, Villarrica in Chile line the mountain chain, fueled by melting rock generated deep beneath the surface. In some regions, the plate flattens before plunging deeper, shifting stress inland and triggering powerful earthquakes far from the coast. Beneath it all lies a simple, unforgiving mechanism, one plate forcing beneath another, storing pressure like a coiled spring waiting to snap. Before we continue, don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. The history of this boundary is written in Catastrophe. In 1868, a massive magnitude 8.8 earthquake struck southern Peru, killing around 25,000 people and unleashing a Pacific-wide tsunami that erased coastal towns. Just 9 years later, in 1877, northern Chile experienced another devastating rupture, likely near magnitude 8.5. A powerful tsunami followed, reaching across the Pacific and causing destruction as far as Japan, leaving thousands dead in Chile and Peru. These were not isolated disasters. They were segments of the same immense boundary failing under overwhelming strain. Then came 1960. The southern portion of the margin ruptured in a staggering sequence that reached magnitude 9.5, the most powerful earthquake ever measured. The rupture extended for more than 1,000 kilometers, and the shaking lasted nearly 10 relentless minutes. Coastal land rose and sank by several meters. Entire cities collapsed. Entire forests were drowned as the shoreline shifted permanently. The tsunami that followed crossed the Pacific Basin, killing over 1,600 people in Chile, and dozens more in Hawaii and Japan. 50 years later, in 2010, central Chile endured another enormous rupture, a magnitude 8.8 that lasted for minutes and triggered destructive tsunamis. Buildings collapsed, highways split apart, and millions felt the force. Yet even that event did not release strain along the entire boundary. It ruptured one segment, while others remained ominously quiet. Scientists studying the margin see a clear pattern of segmented failure. One section ruptures, then another, sometimes decades apart. The fault does not give way all at once, but behaves like a chain of locked zones that fail when stress overwhelms them. More troubling still, some stretches have not ruptured in over a century. These seismic gaps are not safe zones. They are areas where strain continues to build. In 2014, northern Chile was rocked by a magnitude 8.2 earthquake. For years, scientists had warned that this stretch of coastline was a prime candidate for a major rupture because it had not broken since 1877. When the shaking began, many believed the long-awaited release had finally arrived, but it didn't. The rupture stopped short. Only part of the seismic gap failed. Large sections of the fault remained locked offshore, directly opposite major population centers. Studies that followed showed that significant strain was still accumulating beneath the ocean floor. The earthquake had relieved some pressure, but not the deepest part of it. The warning signs continued. In 2015, central Chile was struck by a magnitude 8.3 earthquake, triggering evacuations and tsunami alerts. In 2021, a magnitude 7.0 hit off northern Chile, while a magnitude 7.5 inland earthquake shook Peru. These were powerful reminders of an active system, yet none ruptured the largest locked segments of the margin. Between 2015 and 2026, the Peru-Chile Trench has remained restless, producing repeated magnitude 6 and 7 earthquakes, offshore tremor clusters, and measurable crustal deformation. Satellite radar reveals subtle coastal warping, while GPS stations confirm ongoing compression at rates approaching 9 centimeters per year. Off Peru's coast, strongly coupled sections of the megathrust continue storing nearly all relative motion as strain. Lima, a city of nearly 10 million people, sits above sediments that can amplify shaking. Monitoring has never been more advanced, with satellites and seismic networks mapping where the fault is exactly locked. What remains unknown is how long it will hold. The question that lingers over this boundary is unavoidable. Could the Nazca Plate generate another magnitude 9 or greater earthquake? The answer is yes. The margin has already demonstrated its capacity for extreme rupture. More than 40 million people live along the Pacific coasts of Ecuador, Peru, and Chile, directly in its path. Major ports handle global trade, including a significant share of the world's copper exports from Chile. Energy infrastructure, desalination plants, highways carved into cliffs, fishing industries, and dense urban neighborhoods line the shoreline. A massive rupture along a strongly coupled segment could produce intense shaking lasting several minutes, overwhelming older structures and testing even modern engineering. The threat does not end with the shaking. A megathrust earthquake would displace enormous volumes of seawater, generating a tsunami capable of striking coastlines within minutes. Coastal cities would have little time to respond. In deep water, the tsunami would race outward across the Pacific at jetliner speeds. Hours later, distant shores could feel its force. There is also the unsettling possibility of cascading rupture. If one locked segment fails, the sudden release of stress can shift to adjacent sections, allowing the rupture to propagate farther than expected, tearing through multiple segments in sequence. The 1960 event showed just how long this boundary can tear. Under the right conditions, the tearing could continue. The magnitude depends on how much of the fault fails at once. On a 4,000-kilometer margin, the potential scale is enormous. Chile has invested heavily in earthquake-resistant building codes and tsunami warning systems. Early warning networks can detect the first, less damaging seismic waves and send alerts seconds before stronger shaking arrives. Peru and Ecuador are strengthening infrastructure and expanding monitoring networks. Across the Pacific, tsunami warning centers stand ready to analyze seismic data and issue advisories. But preparedness has limits. Early warning offers seconds, not minutes. Sirens can signal evacuation, yet coastal communities often have little time to reach safety. Monitoring systems can measure accumulating strain, but they cannot release it. They can observe the coiled spring, not unwind it. Modern technology has made the danger more visible than ever. Scientists can map locked offshore zones and estimate how much stress has built since the last rupture, yet the exact timing remains unknowable. Earthquakes do not follow human schedules. Communities along this margin live with a dual reality. They know the risk. They have experienced great earthquakes before. And yet daily life continues. Markets open, ships depart, children walk to school. The horizon looks calm. Beneath that calm, two plates remain locked together. Subduction zones move in cycles measured not in months, but in decades and centuries. Energy builds as plates converge, then releases in ruptures that reshape coastlines and alter lives before the process begins again. The Nazca Plate has repeated this cycle throughout recorded history. Today, it is still advancing at nearly 9 centimeters per year. Portions of the boundary remain locked, and strain is measurable. The same margin that produced the largest earthquake ever recorded is still active. The conditions that allowed a magnitude 9.5 have not disappeared. They remain beneath the ocean floor and the cities above it. No one can predict whether the next rupture will be an 8 or something greater. What is clear is that the system is not dormant. Along Ecuador, Peru, and Chile, the continent continues to bend almost imperceptibly. The margin is quiet, but it is not asleep, and the engine beneath it is still running. And when it releases again, it will not ask whether we are ready.